Welcome, everyone. Today, we are going to dive deep into a major transformation happening right now in artificial intelligence research, the paradigm shift from static large language model reasoning to what is known as agentic reasoning. For a long time, we have thought of reasoning as the core of intelligence, the ability to infer logically, solve problems, and make complex decisions. And large language models, or LLMs, have shown incredible, unprecedented leaps in these areas over the past few years. Think about how they can solve complex math problems or write intricate code. Techniques like chain-of-thought prompting have heavily boosted their performance by forcing the model to explicitly state its intermediate steps, essentially giving it computational space to think before answering. However, there is a fundamental catch. These successes are largely confined to closed-world domains. These are static environments where the question is fixed, and the model merely needs to generate an answer in one go. In the real, open-ended world, information changes rapidly, environments are incredibly dynamic, and true intelligence requires you to act, adapt, and learn over time. Conventional LMs are, at their core, passive sequence predictors. They are not built for continuous, grounded interaction with an evolving environment. This critical limitation brings us to our core topic today, agentic reasoning. What exactly happens when we reframe large language models not just as passive text generators, but as autonomous reasoning agents? Instead of relying solely on its static internal parameters to generate text, an agentic system reasons through action. It can independently invoke external tools, explore alternative paths, update its internal memory, and seamlessly integrate feedback from its environment. We are essentially moving from a system that thinks and answers to a sophisticated system that plans, acts, perceives, and adapts. The foundational paper we are synthesizing today organizes agentic reasoning into three complementary layers. First, foundational agentic reasoning, which involves core, single-agent capabilities like planning, using tools, and searching for external information. Second, self-evolving agentic reasoning, where the agent improves through cumulative experience, utilizing feedback and memory to refine its own reasoning over time without full model retraining. And third, collective multi-agent reasoning, where we scale from isolated solvers to collaborative ecosystems of specialized agents working together. Across all these three layers of agentic reasoning, the research identifies two primary optimization modes. The first is in-context reasoning. This optimization focuses on scaling inference time compute. We orchestrate the agent dynamically using structured workflows and prompts, directing its reasoning process without ever changing the underlying model parameters. The second mode is post-training reasoning. This involves actually training the model weights to internalize these agentic strategies. This is typically achieved via reinforcement learning or supervised fine-tuning, embedding the ability to plan and act directly into the neural network architecture. To truly understand this profound shift in artificial intelligence, let us look at it through a more formal control-theoretic lens. We can mathematically model the environment the agent operates in as a partially observable Markov decision process, or POMDP. In a traditional LLM setup, the model policy takes an input and generates an output sequence. But in an agentic system, we introduce a critical new component, an internal reasoning variable. The policy of an agent is now factored into two distinct sequential parts. First, the internal thought or reasoning policy. The agent processes its history, observations, and internal memory to generate a hidden reasoning trace or a concrete plan of action. Second, the external action policy. Conditioned explicitly on that internal thought, the agent then commits to an action in the real world, like navigating a web page, calling an API, or returning a final answer to the user. This separation between thought and action is absolutely crucial. It highlights the think-then-act structure that defines agentic systems. We are no longer just mapping inputs to outputs. We are performing deep computation in a latent reasoning space before committing to an action space. This structural shift is precisely how artificial intelligence reasoning transitions from static prediction to interactive, highly adaptive intelligence.